Assalamu alaikum and have a very good day, everyone. First of all, thank you so much to the organizers of the conference, Quantum Meets AI 2026 from Qubits to Quantum Advantage, for inviting me as a speaker. It's truly an honor to be part of this conference and to connect with such brilliant minded community. Starting with my introduction, my name is Abubakar Siddiq and I did my bachelor's in computer software engineering from UT Peshawar and then my MS from JIK Institute of Engineering Sciences and Technology. Currently, I am a PhD student at the University of Manitoba, Canada. Before I begin, I would like to sincerely apologize for not joining you live today. Due to the significant time zone difference and my commitments in the lab here at my university, I was not able to present it online. But at the same time, I didn't want to miss the opportunity to share my limited knowledge with you, so I recorded this talk instead. Before I start the presentation, I would like to express my special thanks to Professor Dr. Fazl Khalid, Worthy Rector JIK Institute, Professor Dr. Syed Muhammad Hassan Zaidi, Pro-Rector JIK Institute, for his constant and exceptional focus on exploring emerging technologies. I would also like to extend my special gratitude to my supervisors, Dr. Khurram Khan Jadoon and Dr. Tahir Naseem, for their exceptional guidance and motivation in the field of quantum computing and deep learning. So let's begin with the topic, which is Introduction to Quantum-Based Deep Learning. I want to start with the quote that I found in an article, Will Quantum Be Bigger Than AI? In which a BBC journalist, Zoe Kleinman, wrote that you can either explain quantum accurately or in a way that people understand, but you cannot do both. I like this because it's basically a warning for a talk like this. So let me be honest with you in advance. Today I'm going to pick the second option. I'm going to explain the things in a way that makes sense, even if that means I skip some of the heavy mathematics. If you are a physicist, please forgive me. Today I am going to focus on giving you the intuition and not the mathematics and equations. So the first question is, why do we need quantum-based deep learning? While deep learning is already amazing and already matured, it gives us ChatGPT, image recognition, self-driving cars, and many more. So why do we bring quantum into this field? The answer is that deep learning is starting to hit some real limitations. The first one is cost. Training just one of the bigger frontier AI models can cost over $100 million. That's only one model. So the second one is energy. Back in 2022, data centers used about 460 terawatt hours of electricity. And because of the AI boom, the number is expected to be doubled by 2026. I don't have the current data, but that's really a huge amount of power. The third one is there are some specific problems which classical computers simply can't handle well. For example, simulating molecules and new materials. The mathematics becomes so heavy and normal computers cannot simulate. Now here is quantum gets interesting. Look at this number. Just 300 qubits can represent more states than there are atoms in the entire observable universe. So this is the hope. Maybe we can represent very rich, very complex patterns using only a few qubits. So this is the dream driving this whole field. Okay, so when we combine quantum computing and deep learning, there are basically four different ways to do it. And it is based on two things. The first one is my data classical or quantum? For example, images and text are classical data, but the output of a quantum experiment is quantum data. The second question is my computer is classical computer or quantum computer? So by combining these, we get four combinations. The first one is CC, which is classical data on classical computer. That's just normal deep learning. So what we do today, technically it is not a type of quantum deep learning, but I just put it here to have a complete picture of all the four types. The second one is CQ, which is classical data on quantum computer. The third one is QC, which is quantum data on a classical computer. And the last one, QQ, is quantum data and quantum computer. That's the fully quantum pipeline. For today, the important one to remember is CQ, the green one you can see, which is classical data on quantum computer. That's the most practical one right now, and most of the papers and articles are available on this type of quantum deep learning. We take normal data like images and feed it into quantum system. So here is a simple way to think about it. A quantum computing and deep learning developed into different worlds. They use different concepts, different tools, and even different ways of representing information. But the reason that lets them combine to each other is that they actually share the same mathematics, which is linear algebra. Deep learning is built on it, and quantum computing is built on it. So even though they look very different on the surface level, but in deep down they are using same mathematics, which is linear algebra, and that shared language is exactly what makes it possible to bring them together. So let's go through 3 key concepts of quantum deep learning. The first one is hybrid computation, like how quantum and classical computers work together in one pipeline. The second one is variational quantum circuit. This is the actual quantum, I would say a brain that learns. And third one is quantum transfer learning, an approach that makes all of this practical today. So let's discuss one by one. So let's start with the hybrid computation. The main thing to understand is that today's quantum computers are not perfect. They are still small in scale and affected by noise, which means they can make errors. We even have a name for this current era of quantum computing, NESQ, which stands for noisy intermediate scale quantum. As quantum computers are not yet fully reliable and powerful enough to work independently, we do not use them alone. Instead, we combine them with classical computers. This is the idea behind hybrid quantum classical computation. The quantum part is called quantum processing unit. You can think of it as a specialized processor that performs specific quantum operations. The classical computer handles the rest of the tasks, such as data processing, optimization, and controlling the training process. These two parts work together in what we call quantum classical loop. The quantum circuit runs and produces an output. Then a classical optimizer, which is a standard optimization algorithm, analyzes the output and updates the parameter of the quantum circuit. The process is repeated again and again until the model reaches better performance. This complete framework, where a quantum circuit is combined with classical components, is called dressed quantum circuit. Simply imagine the quantum circuit at the center, surrounded with classical layers that help prepare the input and process the output. So now the main part, the variational quantum circuit. Also we can say VQC. This is the part that actually learns. Let's go through it step by step. So the first one is encoding. Like over data, like in image or text, like in image is just like normal numbers of pixel value. But a quantum computer cannot read normal numbers directly. So first we have to translate the data into quantum world, quantum domain. I mean qubits. That translation step is called encoding. There are different ways of angle encoding, amplitude encoding, and many more. And every approach has its own advantages and disadvantages. So which one is where to use is totally, this is a research area. I'm not going into the details of those encoding steps, that how it works, but simply you can say that encoding is the conversion of data from classical domain into quantum domain. So insert looks like a fancy word, but the idea behind it is quite simple. It basically represents the structure or design of our quantum circuit. Like you can think of it like the architecture of a neural network or the skeleton of a model. It defines how the quantum gates are arranged, how the qubits interact with each other, and how the information flows through the circuit. So just like in deep learning, where we choose different network architectures, such as CNNs or transformers, and many more, in quantum computing, we also need to define the structure of our quantum circuit, and the structure is called inserts. So trainable parameters inside the quantum circuit structures, we have adjustable parameters, we have learnable parameters that are optimized during the training process. These parameters control the behavior of the quantum gates and determine how the quantum circuit transform the input information. If you are familiar with classical deep learning, you can think of these as the weights of a neural network. The concept is very similar. In classical deep learning, learning means updated the weights of the network to improve its performance. Similarly, in quantum models, learning means finding the optimal values of these trainable parameters so that the quantum circuit can perform the task, the desired task. During the training process, an optimization algorithm continuously updates these parameters by minimizing the loss function and gradually improves the performance of the model. So now entangling layer, this is one of the most important parts of a quantum circuit. Entangling layers allows qubits to interact with each other and create a correlation between them. This means that the state of one qubit can become connected with the state of another qubit in a way that is fundamentally different from how classical bits work. In simple words, entanglement allows qubits to share information and work together as a quantum system rather than acting independently. This interaction between qubits is one of the main features that gives quantum computing its unique capabilities and makes quantum models different from classical approaches. Now measurement, at the end, we look at the qubits to get an answer, to get a number. But here is a strange thing happens. As we know, quantum is random. It is totally based on probability. So we actually run it many times to take the average to get a answer, reliable number. The number of times we run it is called shorts. Like shorts is a word which we use in the quantum computing. So cost function then the number or the answer which we get from the measurement goes to the cost function, which just measure how wrong the answer is. The bigger the mistake, the bigger the cost. Now there is one important challenge. In classical deep learning, we improve the model using a technique which is called backpropagation, which calculates how each weight should be updated to reduce the error. But this approach does not directly work in the same way for quantum circuits, especially when running on quantum hardware. Therefore, we use in alternative methods to calculate the gradients of the trainable parameters. One of them commonly used method is parameter shift rule. In simple terms, we slightly change a parameters in the quantum circuit in the positive direction and then in the negative direction. By observing how the output changes in both cases, we can determine how the parameter affects the final result. This information tells the optimizers in which direction to update the parameters so that the quantum model gradually improves its performance during training. And finally, the classical optimization loops, which is classical computer updates all the parameters and we repeat the whole things again and again until the circuit learns. So now quantum transfer learning. This concept is important because it makes quantum machine learning more practical with today's available technology. The main challenge is that current quantum computers are still very limited in size. They have only a small number of qubits, so they cannot directly process large real-world data, such as high-resolution images or lengthy sentences. So with thousands or millions of pixels in high-resolution images. So the idea is to combine the strength of both classical and quantum computing. Instead of asking the quantum computer to handle the complete task, we first use a large pre-trained classical neural networks to extract meaningful feature from the input data. This classical network performs the heavy feature extraction and compresses the original data into a much smaller and more informative feature representation. Then these extracted features are passed to a small quantum circuits which perform the final processing on classification task, or I would say regression task, whatever we have in hand. If you remember the idea of addressed quantum circuits that we just discussed earlier, this is exactly where it is applied. A classical neural network is placed in front of the quantum circuits, and together they form a hybrid classical quantum model. So there are three main types of quantum transfer learning approaches. The first is classical to quantum, where classical features are provided as input to the quantum circuits. This is currently the most practical and widely used approach. The second is quantum to classical, where quantum features are extracted first and then processed using a classical model. The third is quantum to quantum, where both features extraction and processing are performed using quantum models. This approach is more future oriented as quantum hardware continues to improve, continues to mature. For current quantum devices, CQ, classical to quantum, is the most practical approach because it allows us to combine powerful classical deep learning models with small scale quantum computers and apply them to real world problems. So now you might be wondering, do we have to build all of these quantum circuits from scratch, from start? Fortunately, the answer is no. Today, there are several powerful software frameworks that makes quantum machine learning much easier to develop. These libraries provide built-in tools for creating quantum circuits, training quantum models, and integrating them with classical deep learning frameworks. One of the most widely used frameworks is Pennyline, which is especially popular for quantum machine learning because it integrates seamlessly with PyTorch and TensorFlow, and allowing us to build hybrid classical quantum models using tools that many deep learning researchers are already familiar with. The second important framework is Qiskit machine learning developed by IBM. In addition to simulation, apart from simulation, it also allows us to run quantum circuits on real-time IBM quantum hardware through the IBM quantum platform. The third useful framework is Torch Quantum, developed by researchers at MIT. It is designed with a PyTorch-like interface, making it particularly convenient for researchers who already have experience with PyTorch. So if you are planning to start learning quantum machine learning, I would recommend beginning with Pennyline. It has excellent documentation, integrates very well with PyTorch, and provides several ready-to-use tutorials, including tutorials on quantum transfer learning, which make it great starting point for beginners. So there is a lot of excitement and hype around the quantum computing today. You may come across headlines claiming that quantum computer will revolutionize artificial intelligence. But the reality is a bit more complex. At the moment, quantum deep learning does not consistently outperform classical deep learning. In many research studies, hybrid quantum classical models achieve performance that is comparable to well-designed classical model, but they do not necessarily perform better or outperform. Another important point is that in most hybrid architectures, the classical neural network still performs the majority of the computation. It extracts the features, processes the data, and reduces the dimensionality before passing a small set of features to the quantum circuit. So the question is, how much does the quantum component contribute today? So I think the honest answer is that this is still an active area of research, and we are continuing to investigate its true advantages. So I think this is why I believe that the best way to view quantum deep learning today is a proof of concept and is a research platform. It allows us to explore how quantum circuit can be integrated with deep learning, evaluate their behavior on real world data sets, and understand where they may provide advantages as quantum hardware continues to change. So while we are not yet at the stage where quantum deep learning consistently outperforms classical deep learning, we are building the foundation for that in future. And perhaps that is the most exciting part. We are still in early stages of this field. Many important questions remain unanswered. Many challenges are yet to be solved. And the next major breakthrough could come from any researcher, including someone sitting in the audience today. So I think that's it from my side, and thank you all for your time and attention. If you have any question, comments, or like to discuss any of the related topics, please feel free to reach out to me through my email address. I would be more than happy to answer your questions, exchange ideas, or continue the discussion. Once again, thank you to the organizer of the conference, Quantum Meets AI 2026 from Qubits to Quantum Advantage, for giving me the exceptional opportunity to be part of this prestigious conference. Thank you very much, and I wish you all a wonderful conference. Have a great day, and goodbye.